Yeah.
Jules, yeah, take it away.
Okay, I'm a little bit alarmed about how much I want to get through today, so let's see how this goes. So I'm gonna save some time by slightly rearranging. So I was about to show you that categories and spans are compact closed. I'm going to instead tell you what is a hypergraph category, tell you that hypergraph categories are compact closed, and then tell you that spans are a hypergraph category. So that kills two birds with one stone. And in fact, I'm going to do it for cospans instead of spans because I also need you to know what cospans are. Yeah, sorry. So a hypergraph category. So here's the general idea. In a monoidal category or a symmetric monoidal category, we draw string diagrams, and this is a kind of linear world. The reason it's a kind of linear world, so every output has to connect to exactly one input, and this is because in the string diagram you have something like conservation of string number. Every piece of string that begins in one place has to end in exactly one place. It can't stop existing, and it can't become two pieces of string. If we have a bunch of comonoids around, so for example, if we're in a Cartesian world, or if we have a supply of comonoids, then we can have one-to-many connections. So one output can connect to many inputs by copying. But still, we have this kind of causality, the progressivity condition, which is the kind of causality that says that we can only connect to inputs that come strictly after. In a traced category, we say that any output can connect to any input. Right, we can connect back to an input that was in the past in the causal ordering. Then we went to a compact closed world, and kind of all bets are off for causality. We can connect basically anything to anything else. The concept of inputs and outputs basically goes away. So now we have a division into a kind of a left boundary and a right boundary, but that's basically an arbitrary distinction now. That's just so that our things can be morphisms of a category. It's helpful. It's helpful for very deep reasons to have a distinction into exactly two boundaries, left and right. But it becomes like we lose the causality of input to output. Yeah.
Sorry, so is compact closed or less causally behave and trace?
Yes, I would say so. Yes. I don't know if I can justify that. It's sort of a vibe trace. So trace still behaves. So many trace categories still behave like they have an arrow of time, but they have an arrow of time that admits non-well-founded recursion. But categories of programs or computable functions are still traced. So in a computable function, you have a causality from input to output. Now, hypergraph, this is kind of the most relaxed form of this. This says that we can connect arbitrary things to arbitrary other things in a many-to-many way. So hence the name hypergraph, right? So instead of pieces of string that connect one thing to one thing, we have like blobs of stuff that connect any number of things. But it has a very neat definition. So it's a symmetric monoidal category plus supply of commutative comonoids and monoids satisfying some equations. So we already have the comonoid equations and the monoid equations, and I'm going to additionally say, one thing I'm going to say is if I have my monoid unit and I connect it to my comonoid unit, I get this thing, which is the identity on the monoidal unit. And then so that's called the bone equation. And then the other thing is that, yeah.
Is the monoid unit commutative as well?
Yes.
Oh.
There are non-commutative versions of this, but I'm not talking about those. And then the thing which is called the Frobenius equation says that. Wait, hang on. I need to look at this. Okay. And the other one, which is okay. Then So a pair of a monoid and a comonoid commutative that satisfy these, this is called a Frobenius algebra. And this is called the Frobenius equation. Often we will have one extra equation which says that if I do that, it's the same as an identity. And if I have that, this is called a special Frobenius algebra. This is called the special equation, which is a terrible name. I did not name this, I promise. Yeah.
In this equation, there's like no kind of going back.
Correct. Yeah. So everything is, yeah. So equivalently to this, I can say that I have a supply of things of this form, where I have m greater than or equal to 0 things here, and n greater than or equal to things here. This is called a spider. So we have a supply of spiders, and they have to satisfy the spider fusion equation, which says that so two spiders that connect by a non-zero number of legs is the same thing as a single spider with lots and with even more legs. This is called spider fusion. So this, if you have all of these equations, this is a kind of another thing where you have a neat unbiased version. So this, you can think of this as a kind of topological view. And then it happens that you can finitely axiommatize it with these things called Frobenius algebras. But the general idea is, so you can think of this as like a hyperedge that connects all of these things together. So now if I have a string diagram, I can just like use one of these structures to just connect anything I want to anything else I want in a many-to-many way. Okay. So the reason I'm telling you this is that these things are also really common. So my favorite example, again, RAL with tensor product has these. I'm going to show you that categories of cospans have these. Categories of spans also have them. First, I'm going to say that every hypergraph category is compact closed. So again, we have this hierarchy, like every compact closed category is traced, and every hypergraph category is compact closed. But we get kind of fewer examples each time. So, namely, if I have a Frobenius algebra, then I can define this to be this, and I can define this to be this. So that's the monoid unit followed by the comonoid multiplication. This is the monoid multiplication followed by the comonoid unit. And it turns out that this thing satisfies the equations to be a compact closed category. So if I do a snake like this, I was defining this to be this, and now I can apply the Frobenius law and find that this is the same thing as this, and then I can apply my monoid and comonoid equations. Okay. Yes. I'm sure there was something I wanted to say. But it's fine. Okay. So, I mean, the intuition for this is very strange now, right? I mean, the intuition for these was really strange. If you think about the kind of causal flow of information in the diagram, you can't really do it, or in general, you can't really do it. And now this is even more strange. This is like, to turn a value around, we like magically pick a value from nowhere and then copy it. So, like, the closest thing you can do is that in the category of REL with tensor product, you can give an interpretation of this computationally as non-deterministic computation. So, in REL, you can say, like, this thing sort of is like I don't remember the exact terminology for control structures. I'm just going to say checkpoint. This is a backtrack point. this is like shift and reset type things. I say like x is I have some way of choosing an arbitrary value in a non-deterministic way, and then I return xx, and then this thing is like, well, I input some x prime, and I say if x equals x prime, then I'm done, else backtrack. And by backtrack, I mean go back to the checkpoint and try to choose something else arbitrary and just keep doing it until I get the answer I wanted. So like rel is an example where you can get some kind of causal interpretation. It's some kind of like basic logic programming. Where I can do some kind of backtracking stuff. So rel tensor is kind of like Prolog without the weird bits. Okay. And you can see here, like this sort of does this decomposition that I'm choosing an arbitrary x, so that's like I'm choosing an arbitrary x and then I'm returning it twice. Okay. And here I'm checking. So the corresponding unit is fail if not equal. If they're equal, return it, and then I delete it. Okay. Cool. So now I want to tell you about cospans and show you that cospans have this structure, and then that's building onto what we're doing next. So I showed you earlier what spans are. Cospans are the same thing with the arrows reversed. So cospan set is a category where objects are sets, and a morphism from x to y is a diagram like this, where now the arrows go this way. So these are in some ways like spans and in some ways totally different. So now how do I compose these if I have another one? Well, I do it by now push out. So I do A plus Y, B. And again, you can do this whenever, if I have any category which has all finite colimits now, and in set I can calculate what this is, that this is like a quotient of this is a quotient of A plus B. I quotient out the stuff that agrees on Y. Calculating universal properties in set in particular is like very easy once you get used to it. Okay, so I want to show you that this is a hypergraph category. For example, well, so I want to have a so I need to tell you that the monoidal product comes from disjoint union of sets. That's an important thing. So what I want is a cospan from x to x plus x, and I think the thing I want to do here is have x, and then I have this, and I have merge. If I have an x or an x, I still have an x. And my co-unit is so my monoidal unit now is the empty set. So I now want to do x here. Yeah, so I have a universal map here, and I have an equality there. And the thing about cospans and also spans, right, is they're symmetrical in the sense that I can just flip them around. It's a thing called a dagger category. Is like I have an involutive map of morphisms that says that if I have a morphism one way, I can turn it into a morphism in the opposite direction just by reversing it. Like in rel, if I have a relation from x to y, I can have the same relation but consider it going from y to x instead because it's the same relation. So I can just reflect this diagram and it's still a diagram. So I can reflect these, so I get a monoid. And if I work it out, it turns out that these things satisfy all of the equations to be a hypergraph category. So what that means is I can draw string diagrams in this category of cospans, and I can draw string diagrams in this category of cospans and just connect anything to anything else as I like. Okay. Now, coming up, there's two different, we kind of have a fork in the road, and there's two different things I want to cover, but they can do in different orders to each other. So I think I'm going to talk about bialgebras and speed run to ZX calculus in 5 minutes, if I can. That's just so I can tell you what ZX calculus is. It's kind of neat that you can do it in 5 minutes. Is there any questions at this point? Okay. I told you, so Frobenius algebra, or aka the thing that you have a supply of for a hypergraph category, is a particular way that a monoid and a comonoid can interact with each other. But there is one other way that a monoid and a comonoid can interact with each other, which is called a bialgebra, or sometimes called a bimonoid, but I'm going to call it a bialgebra. It's the definition, bialgebra on an object. Again, in a symmetric monoidal category, and it's going to be a commutative. Everything is commutative for me. On an object is a monoid, which I'm now going to switch to drawing these with white circles instead of black circles, plus a comonoid. Like this, satisfying. So now we have some different equations. What I'm going to require is that each is a homomorphism of the other. So I'm going to say that if I have my monoid unit and I copy it, it's going to be the same as that, and the reflection of that. And then if I have monoid multiplication and I delete it, that's going to be the same as deleting both inputs. So we have these and their reflections, and then we have the thing that's called the bialgebra law, which says that if I have this shape, this is the same as, so this is like, think I have a monoid, right? So this is like, I have AB, I have A times B, and then I output A times B twice. So I can copy both inputs, swap them past each other, and now multiply. Yeah. Sorry. Well, so this is set up so that it's actually unambiguous, but in this case, the two on the right are white and the two on the left are black. So in general, so this is the kind of graphical mnemonic that I use. Is if it's a filled circle, it's glorified copying. If it's a non-filled circle, it's doing something computationally non-trivial. Okay. So like applying an actual monoid operation. Yeah. Okay, so this is actually a bit of a weird. Like this doesn't look like it makes topological sense. So I'm going to give an example. So these things are a bit less common. I'm about to give an example. Okay, here's one example. If you have a Cartesian category like set and you have a monoid object in it, so a monoid object in set is a monoid. If you pair that together with the copy comonoid, they satisfy these laws. So every monoid in a Cartesian category is a bialgebra. That's one example.
Can you say that again?
Every monoid in a Cartesian category. So if you're Cartesian, you have unique comonoids. If you have a monoid, if you happen to have also a monoid object, then pairing them gives you these equations. This is because in a Cartesian category, everything is a homomorphism of copy and delete, which gives you these equations. Okay. Now I'm going to give an interesting example. So, okay, this is going to escalate very quickly. So yeah.
Is there anything similar you can say about trying to connect the just the one equation and
Yeah, I think you also, yeah, sorry, I think you do also have this. Yes, I think that's right. Yeah, because that says that each is a, sorry. I think that's right. I don't think I wrote that in my notes. Okay. I have avoided talking about vector spaces because I think many people in the room are not having mathematical backgrounds and don't know about vector spaces, but we'll try our best. Because I'm going to talk about quantum computing, and quantum computing is really about vector spaces. So, in fact, I mean, there'll be people that might not even know what complex numbers are. But it's okay. If you don't know what a complex number is, don't worry about it. It's fine. That's a prerequisite for having any intuition for quantum at all, but I can't help you with that. Okay. So if I have if X is a finite set, I'm going to say that I have this is the free vector space on X, and it's going to be the set of formal linear combinations. So it's like lambda 1 x1 plus dot 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 plus lambda n xn, where like the lambda i's are in there are complex numbers and the xi's are in X. So these are kind of formal linear combinations modulo the equations that you think that formal linear combinations ought to satisfy. So these things are commutative and stuff. Now, I'm going to take the this thing is a vector space. It's an object in the category of vector spaces. In fact, it's an object in the category of finite dimensional vector spaces. The category of finite dimensional vector spaces is another example of all the stuff I'm talking about. It's a hypergraph category. If your finite set happens to have the structure of a monoid, then this thing also gains the structure of a monoid object in a different way. So what I'm going to do is I'm going to take the two-element set of Booleans and I'm going to take the XOR operation. In fact, this is not just a monoid, this is a group. It's the group of integers mod 2 with addition. That's how a mathematician would say it. So this thing, so as a vector space, this thing is just the two-dimensional vector space. It's the set of pairs of it's the set of all pairs of complex numbers. So it's the set of lambda 1 times false plus lambda 2 times true, where lambda 1 and lambda 2 are in C. But because the Booleans is not just a set, it's a monoid. With this XOR operation, I gain an additional monoid structure on this vector space by linear extension. So what this means is that I define it that way on this and this, and I say that all of the laws of algebra still work the same. So I'm going to say that plus C plus D true is, and then I say that this thing should be like A, C, F plus F plus, and so on and so on, right? That's now multiplication of complex numbers.
Oh, right.
Right, A, B, C, and D are complex numbers here. So yeah, this is a bit confusing because there's two different things going on. There's formal linear combinations, but non-formal, honest-to-God complex numbers. Okay, I'm skipping heaps of details here, but in the end, what we get is in the end what we get is yeah.
Does this give the quaternion?
It does not give the quaternions. No, that's something else.
It looks
No.
like that, right?
No. This gives you C squared as a complex vector space.
Oh.
So I can say the scary word. This is the qubit space. So in other words, the state of a qubit is a vector in this space. So what this means we end up with is a monoid like this, which comes, so we got this automatically. This comes from copying X. Then we get this, and this comes from XOR, and plus units, plus a black unit and a white unit, and a black co-unit and a white co-unit. So we have all this structure, and what it turns out is that the combination of a black thing and a black thing is a Frobenius algebra. The combination of a white thing and a white thing is a Frobenius algebra. The combination of a black thing and a white thing is a bialgebra, and the combination of the other way around, black thing, white thing, black thing is a bialgebra. So we get this kind of four-way square where two sides are Frobenius algebras and two sides are bialgebras. And then we get one other thing, which there is a magical morphism, which is called the Hadamard gate, which goes from C squared to C squared. And it has the property that if I have a black thing, its square is the identity, and it transposes between the black structure and the white structure. And vice versa. Okay, that was a speed run to ZX calculus. So what this is a formalism for talking about quantum circuits. So the things that you can, the diagrams that you can draw with this are the things which you can build as a quantum circuit. People actually build these things in the lab, right? So quantum circuits are basically programs that you can run on a quantum computer. You have like a whole bunch of, so each of these are the qubits, and you have a bunch of stuff that you can do with it, one after the other, and then you get a bunch of qubits out. And that's, I mean, I'm skipping all of the physics and all of the engineering, but that's the TLDR of how a quantum computer works, or what it does. It applies quantum gate to a bunch of qubits. So, for example, the most important quantum gate is a thing called controlled NOT. So controlled NOT, it's a map from C4 to C4, and it would normally be written in old school quantum circuit notation like this. But in ZX calculus, it factors that it's a black structure on the top and a white structure on the bottom, like that. Okay, how long did that take me? Exactly half an hour. Okay, that's good. This was not exactly intended to make sense. This was intended to speed run to ZX calculus, so I can tell you what ZX calculus is. Okay, this is lazy shorthand for quantum computing. People draw it that way. That's because your category is compact closed. So left to right is a vibe anyway. You can write this without loss of generality, and any way that you can make sense of it, they're all equal to each other. There's some deep theorems there that when you have a hypergraph category, this thing is actually made of hypergraphs, like in the graph theory sense. Okay, cool. That's a whole load of stuff. I would say any questions, but like I don't think any of this made sense. That's okay.
So does that mean that you can use the black co-multiplication, the white multiplication, or the black co-multiplication, white multiplication?
And they all give you the same result, yeah. Yes. These things, I understand that from an engineering perspective, they're different. Some are easier to work with than others. So in fact, so Okay, a little bit of real applied category theory. How ZX is used in practice. You have some people who want to run a program, and on the other end, you have some engineers who say that this thing will cost you like $10 million, but this thing will cost you $100 million. And you would really like to prove that the thing that would cost $100 million is the same as the thing that would cost $10 million. So I don't know how much quantum computers cost, but it's quite a lot. So like the algebra of, so it turns out, so quantum circuits turn out not to be finitely axiomatizable, but they factor through ZX calculus, which is finitely axiomatizable. So it turns out that, but on the other hand, you can draw things in ZX calculus that are not physical. They don't correspond to a circuit you can run. So going this way to this way is by straightforward, like recursive definitions. Going this way to this way is called circuit synthesis, and it's a hard problem that lots of people are working on. So how, given a ZX calculus diagram, find a quantum circuit. So like the individual, the black structure and the white structure don't correspond to things which you can build in a lab. Only this particular combination of them and various other particular combinations of them correspond to things you can build in a lab. Okay. Cool. I'm not a quantum person. I'm friends with a bunch of quantum people. Okay, let's talk about structured cospans. This thing is the category of directed graphs. So it's and graph homomorphisms. If you didn't know, this is an extremely nice category because it turns out to be the category of functors from a very special. There's a very particular category which has two objects, which I'll call. Sorry, it's not right. I'll call E and V, and two morphisms, two non-identity morphisms called S and T. Like this is a category with two objects and two non-identity morphisms, and a functor from this thing to set is the same thing as a directed graph, and a natural transformation between them is the same thing as a graph homomorphism. Like if you think about it, this is saying that, so a functor from this to set is saying that I send my object E to a set, which I'll call the set of edges. I send my object V to a set, which I'll call the set of vertices. And then I have to send S and T to functions from the set of edges to the set of vertices. And everything magically works out. What that implies is that this thing is a topos. So it has like every nice property ever. It's a model of higher order logic and stuff. Okay, that was just a sideline because it's a nice category. You should know that. Okay. For this purpose, for today, I'm also going to pretend that all graphs are finite. Everything I said is still true. As long as you believe that the category of finite sets is a topos, then you're okay. Right. That I don't really need to assume finiteness. It just avoids, like, infinite graphs are kind of weird. Somehow we are okay with infinite sets, but I think infinite graphs are a bit weird. But it doesn't really make a difference at all. Okay. There is a functor from fin set to graph, which takes every set to the graph which has those vertices and no edges. This is the discrete graph on a set. It's a graph with no edges. So there's an adjunction between fin set and graph. F. Actually, instead of U, I should call it V because it gives you a set of vertices, right? Throws away the edges, and that's a left adjoint. Okay. So think about cospans in graph. Okay, because we know the graph is a topos, we know it has push-outs. And later I'm going to start calculating push-outs, but we'll come to that. But think about cospans in the category of graphs, whose feet are in the image of F. So they're discrete graphs. So I'm going to say I have the discrete graph on some set X, I have the discrete graph on some set Y, and then I have my graph. And then I have two graph homomorphisms like this, which are called L, R. So what is this thing? Well, it's a graph, a directed graph, whatever. I'm just going to, as a directed graph. And then I have a kind of a left boundary. Okay, I'm going to have to draw some more nodes. And then I have a right boundary. And then this says that I have an embedding of my left boundary and my right boundary into the graph. So I might say that this corresponds to this vertex, this corresponds to this vertex, and this corresponds to this vertex. Okay, so this is basically, it's a graph together with some set of vertices which I have called the left boundary and some set of vertices that I called the right boundary. So this is some kind of open graph. The word open graph is a bit slippery. It can have multiple different reasonable meanings. This is one possible meaning of the term open graph. Now, I can basically compose these things just as cospans, as cospans in the category of graphs, and everything works okay. So I can take a push out plus H, Y. What are push outs in the category of graphs? Well, it turns out that they're gluings of graphs that identify the vertices that are here. So this is gluing graphs together. So let's say I have this, and then I have some other graph like so I have here's my left boundary now, here's my right boundary. And now I take the push out. So I'm taking the push out of this graph and this graph along the embedding of this into this and this into this. And what it ends up doing is identifying these two vertices with each other. So I end up getting so now let me think about it. That one's going to there, and then I have this thing. I'm just making this up on the fly, by the way, if this wasn't clear. There we go. And I still have my left boundary from the left component. Hopefully I haven't made a mistake, and my right boundary from the right component. So this is like a category. This is a category whose morphisms are open graphs, and morphism composition is graph gluing. And all of my machinery still works. This thing inherits all of the structure I want from the category of cospans. So this thing is a hypergraph category. The hypergraph structure says that I can glue lots of vertices together. I can just identify things together. It's worth saying what are identity morphisms in this, by the way, because that's important. The left boundary and the right boundary can coincide with each other. They do not have to be separate. And in fact, if you want identity morphisms in this category, they have to be allowed to not be separate. So, so if I have the identity from X to X is going to be a discrete graph, and then I'm going to identify both the left boundary and the right boundary with the same things, and so on. So when I do any kind of gluing, that means that like whatever this is connected to will be identified with whatever this is connected to, because quotients are transitive like that. Okay. And this is how we start to build categories or open systems. So open graphs are something like the most basic kind of open system. This is a kind of I mean, once we start adding more structure to it, it starts to have names like network. Is there anything that I wanted to say that I've skipped over? Is the question. I forgot to say what the monoidal structure of this thing is. The monoidal structure is disjoint union of graphs. So this category has a coproduct, which is disjoint union of graphs. You just stick two graphs next to each other. And that the monoidal structure of this thing, the one that's a hypergraph category, is coming from the underlying coproduct. Yeah. So this thing is called a structured cospan. This is like the prototypical example of a category of structured cospan. So a structured cospan is a cospan whose feet are in the image of a left adjoint functor, and then like, yeah. So, okay, let's talk about semantic functors. So, okay. So a common methodology, what we generally want to do, we want to build some kind of category of open systems. We want to study a thing. So here we want to study directed graphs. So directed graphs are pretty basic, but let's say we want to study directed graphs. We're going to make a category of open directed graphs where, so a hypergraph category whose morphisms are like pieces of directed graphs which we can glue together. We would like, so that's our kind of object of study. And I'm going to think of that as the kind of category of syntax. We have a kind of syntax for graphs. Now I want to talk about some kind of semantics. So I want to say that my objects of study have some behavior, or they do something. They do something that I care about. I want to calculate something about them. So what we generally want to do is we want to functorially map out of a category like this into some other category that we care about. A thing that happens unreasonably often, and I don't have any kind of explanation for it at all, it's like an empirical fact, is that your syntax, your domain, so we're going from syntax to semantics, right? Not the other way around. These things are unreasonably often co-Spanish, and these things are Spanish, not the other way around. That's not my joke. I blame John Byers for that. There's a weird symmetry break that I have no explanation for, but it's an empirical fact, is we virtually always map from categories of co-spans to categories of spans, not the other way around. Don't know why. Like sometimes symmetry breaks like that. So I'm going to motivate semantic functors by giving you a non-example. I'm going to give you something that I would really, really love to be an example, and it fails to be functorial. Namely, so the category I've defined, this category of cospans, I'm going to call it O-graph. So this is the category of sets, finite sets, and open graphs. I would like to define a functor from open graphs to relations, which is reachability. I would like to say that given a graph, I have a relation that says when a vertex in the left boundary can reach an object in the right boundary, that there is a path from here to here. So on objects, I'm going to be the identity, and then to be the relation And actually, if I'm being careful, I have some function here, some function here. So I want to say that L of x reaches R of y in G. Seems reasonable. This turns out not to be a functor. And I will explain why, because I find this kind of illustrative of the kind of things that can go wrong. This is why life is not easy. So the minimal counterexample. The minimal counterexample says we're going to have a graph from one thing to three things to one thing. Namely, so here's my one thing, here's my three things, and here's my one thing. And G, I'm going to set to be the following graph. Okay, the boundaries line up as expected. Like the corresponding the boundary correspondence for vertices is the one that's next to it. And I'm going to do that and then that. So that's a directed graph. And now on this side, I'm going to do that and then that. So this is the minimal counterexample to functional reality. Maybe you can see it already. So suppose so. So first of all, let's apply my functor to my non-functor to each of these two pieces, and then compose in rel. So here, I need to now name all of these things, of course. This is A, B, C, D. I think without loss of generality, I can call this B, C, D and get away with it. Yeah, that's fine. And then E. So this is now A, B, C, D, B, C, D, E. So my relation is going to be that A is related to B and nothing else. And here I'm going to have that D is related to E and nothing else. So if I compose in rel, so the definition of composition in rel is, does there exist a thing on the middle boundary such that, so x is related to z if there exists a y such that x is related to y and y is related to z. And you see that there is no point here such that this can reach that point and that point can reach this. But hopefully you can already see, after I glue these together, I get this thing. And now we've basically gained a path. So the relation that we get from A to E actually says that A is related to E. So, you know, this does actually hint at how we can recover this example into something that works. That if we enforce a condition that says, like, I think things like left boundary vertices can only have outgoing edges and right boundary vertices can only have incoming edges. I'm not sure if it exactly works. I think it works. I started writing it down in my notes and I was like, I'm not sure this works. Yeah. So this is a very classic example of something that I would love to work and doesn't. So I call this an emergent effect, and it's maybe disingenuous to call this an emergent effect, but this is something like a behavior of the composite that doesn't derive from behaviors of the whole of the parts, as long as your notion of behavior is naive enough. Of course, the reason why we would like a functor, I mean, other than functors are nice, is that it would actually give us an algorithm. So if we have some big complicated graph and we want to know, can we get from here to here, then I have a divide and conquer algorithm, namely I can carve this graph up into pieces, calculate reachability for each of the pieces, and then stitch them back together. So in other words, to compute f of f g, compute f of f of g, where this thing now means composition in the target in the semantic category. So this is the kind of thing we would like to do. We would like to kind of solve problems like this by doing this, but this is hard in general. Like in general, you can't do this because we care about problems that don't have efficient algorithms. Okay. Shall I skip over electrical circuits? I have 5 minutes. I can either talk about electrical circuits or I can talk about decorated cospans. Okay, maybe decorated cospans are important, but electrical circuits are also really a nice example. I'm going to do electrical circuits because that lets me also handwave about graphical linear algebra. So by electrical circuit, I mean a circuit made of just resistors, just to make life easy. So what that actually means is a graph labeled by positive real numbers. So every edge stands for a resistor whose resistance is the label. People have done this for more and more complicated classes of circuits. This is the most simple one possible. You can extend it without much difficulty to something called passive circuits, which include capacitors and some other stuff. Extending it to active components like transistors was much harder, but it's been done. Okay, so we have a category like open circuits. You can construct it in the same way. It's a category of structured cospans where we have a category of labeled directed graphs, and then we take it has a discrete labeled a discrete graph functor, and then we take cospans, and it's fine. So this lets us talk about like stuff like this, right? And then each of these is a resistor. All the papers written by Americans, so they use the American that symbol. The metric symbol for a resistor is a little rectangle. So this thing has a semantic functor to real vector spaces. So now we have real numbers instead of complex numbers, but with the direct product instead of the tensor product. Maybe I didn't mention we were taking tensor product before, but we were taking tensor product before. But now we're taking direct product. The difference is that like R3 direct product R3 is R6, whereas R3 tensor R3 is R9. So it's additive and multiplicative. So this thing's a byproduct on vect. It's like rel in a lot of ways. A lot of these categories are really similar to each other. Like rel and vect are like super similar to each other. Okay, time is ticking. We have a semantic functor. I'll start writing it like this. It takes this now means this is going to be a finite set. This means I have that many wires in parallel. And I double the dimension. And the idea is that for each wire, I'm going to have a variable for current and a variable for voltage. So now, okay, I'm going to tell you what is the semantics of a morphism like this, where we have some label R. That's the resistance. So this thing should be a linear map from R2 to R2. Namely, so we have a current and a voltage, and okay, so there are two different laws we need to apply from like high school electrical circuits. One you probably remember is V equals IR, and the other one is Kirchhoff's current law, which says that the incoming current and the outgoing current are equal to each other. So you have kind of conservation of current. So whatever was the current on the left side had better also be the current on the right side. It can't go anywhere. But then we have a voltage drop caused by the resistor. So it's V minus, and you'd write IR, but now it's the other way around because R is the scalar we're multiplying by. So it's R, I. Okay. And this turns out to be functorial. So if you have a big circuit of resistors, you really can chop it into pieces, compute the voltage and current locally for each piece, and then stitch them back together. And stitching them back together means doing composition here, and composition here is matrix multiplication. So it's something that's kind of tractable to do. Okay, so I did not get to talk about decorated cospans. Decorated cospans is a more complicated and more flexible way of building categories of open systems. I would have had some stuff to say about it. It historically came a bit earlier. It was in my kind of historically revisionist view, Brendan Fong's paper on decorated cospans, the thing I didn't talk about, was the thing that kicked off applied category theory as a field in anything resembling it. It's something that resembles what it is now. Of course, there was heaps of work before that, but that was the first thing that someone said, like, there's a field here. So a lot of things work. So all the category of open graphs I talked about was done first as decorated cospans, and then someone was like, oh, this is much simpler. Or rather, there was a paper by like Walters and Sabadini and somebody in the 80s that had done it first that way, because somebody has already done it first. Always. With decorated cospans, we can do some stuff that we couldn't do this way, often talking about open systems of equations, open differential equations, things like this, stuff where you have variable, like things that involve formal things on some set of variables, and then we can share variables between terms. So there's some cool stuff you can do, but I have to cut something for time, so that lost out. Yep. See you tomorrow.